Okay, so we are finishing up 6.6, and as I had mentioned yesterday, the best thing we can do is to treat trig functions like variables. When we get kind of towards the end of a problem, it's sometimes better to just treat like a sine of theta as just like an x, and then work from there if you needed to do factoring. Today we're going to be looking more at having to use identities. So that will be a little bit different. So we're not going to do as much as this like treating a trig function as a variable today, because the examples are a little bit easier and they're already going to give us factored forms just from the identities that we use. So we're going to start just with some examples. There's no like notes for this. It's kind of just what we've been doing with 6.1 to 6.4 and then applying it to this section. Okay, so for our first example, we have sine of x plus cosine of x is equal to 1. This is something we kind of have seen. Can anyone recall the Pythagorean identity? I need to minimize this.
Sine plus cosine equals 1. Oh.
So our Pythagorean is squared, so sine x plus cosine squared x is equal to 1. So this is kind of close to that, but we don't have the squares. So when we're working with these problems, we need to try and figure out how we can get to an identity like Pythagorean, or even if we have like a double angle, how might we get a double angle or a sum? So for here, well, if I were to multiply both sides, if I were to square both sides, I should say, not multiply, then I would be able to get to my Pythagorean identity. I'm going to fix this parenthesis, it's covering my 1. And then on the left, I'm kind of cheating ahead and just doing the algebra out. This will be sine squared of x. Then I'm going to have 2 sine x cosine x, since it's sine x plus cosine x. And then I'm going to have cosine squared x. And this is going to equal 1. So I now have 2 pieces of information. On the left-hand side, I have sine squared x plus cosine squared x, which I know is just equal to 1 by the Pythagorean identity. I then also have plus 2 sine x cosine x. So I have 1 plus 2 sine x cosine of x. This is all equal to 1. I almost have factors. Remember, if I wanted factors, I'd want things just in parentheses. So like before we had, say, cosine x plus 1 and cosine x minus 1 equal to 0. If I can get factors on the left equal to 0, then I can solve this nicely. Well, I can just subtract the 1. Then I'll have 2 sine x cosine of x equal to 0. So I now have, well, technically I have factored form. So I have sine of x times cosine of x. When I do these, I like to just divide by the 2 on both sides, which cancels out the coefficient. So I'm just left with sine of x equals 0, or cosine of x equal to 0. What angles give me a y-coordinate of 0?
-1 and 1.
What angle's that? So where is my y-coordinate 0?
That's 0 and pi.
0 and pi. Where is my x-coordinate equal to 0?
Negative 1, 1.
Hold on 1 second.
Pi over 2.
Yep, pi over 2 and 3 pi over 2. So these are just using our unit circle and then looking for where the x-coordinate is 0, which is at pi over 2, and also 3 pi over 2, since the period is 2 pi, and then looking for where the y-coordinate is 0, which is right at 0 and at pi. So we technically have some solutions available, right?
I can't see the whiteboard anymore.
You can't see the whiteboard anymore?
No, I can only see you.
Interesting.
Adam, hang up and then call.
Yeah. That's what we had to do last time. I think that was Memphis. Yeah, that's Memphis.
There we go.
Wait till Adam gets back in.
I'm back. It's fine.
You're good?
Yeah.
Yeah, I don't know why that happens. But we thankfully now know that it's just drop out and drop back in and we're good. Okay. So we have 4 solutions, maybe? We're not sure. The reason being, anytime we square a number, we only get a positive. So squaring might give us, I don't know if anyone remembers the term extraneous.
Yep.
Yeah. So when we square, this possibly gives us extraneous solutions. So we actually have to go back and make sure we don't have any of those here. So we're going to take our original equation and then just plug in each of the values. So I have sine x, so sine of 0 plus cosine of 0. I'm going to put a question mark over the equal sign. So sine of 0, we already said that's 0. At 0 cosine, the x-coordinate is 1. This is equal to 1, so this is good. So I'm going to write my actual solutions. So far x equals 0 is 1. Let's look at pi over 2 next. And cosine of pi over 2. Well, I already know cosine of pi over 2 is 0. So this is just plus 0. And my y-coordinate at pi over 2, I'm still increasing right now. So my y-coordinate is a positive 1. So this is 0, 1. So this is also good. So I also have pi over 2 as a solution. I can then do the same for sine of pi plus cosine of pi. However, you might then recognize, oh, wait, now cosine, the x-coordinate at pi is actually negative 1. So this is 0 minus 1. So that won't work. And then at 3 pi over 2, y is negative 1. So we've now gone into the negatives by going to quadrant 2 and quadrant 3. So sine of 3 pi over 2 plus cosine of 3 pi over 2. This is equal to negative 1 plus 0, which is negative 1. So that doesn't work. So we only actually have 2 solutions. The others are extraneous, coming from the fact that we squared both sides of our equation. Any questions with that one?
No.
Okay. Here, 18, 10. I'm actually gonna write horizontally today, just to see how that works. Zoom out a little bit, that way I still have that there. That's not my hand tool. Let's see if we can make that. Okay. I'm going to split this off. Today's really only example. There's no real notes for today other than the examples. And it's just practicing working with identities. I did forget to specify that this should have been from zero to 2 pi. I know yesterday I mentioned with 6.6 we kind of just label them all as 0 to 2 pi, and that's something that's going to be consistent with all the problems. They're all going to be from 0 to 2 pi. So for our next one, we just have sine of 2x is equal to sine of x from 0 to 2 pi. Okay, what identity do I need to use here? I know I can do something on the left. So this is our double angle identity, right? Because I have 2x. If I write this out the long way, this would be, so this is sine of x plus x, so it's also technically a sum. We know that our double angle identity for sine is just 2 sine of x cosine of x, and then this is going to equal sine of x. What would be my next step? Any takers? What would I need to do next with this equation?
Wouldn't 2 sine cosine x change to something?
Nope, so we already used our double angle identity.
Oh.
So we had sine of 2x and we used the double angle identity, so we're getting this in terms of like very simple sine and cosines, which is great. We want just sine of x and cosine of x, if possible. If this was sine of 2x equals 0, we saw things like that at the beginning of 6.6, where it's just inspection, and then I just said, this is sine of 2x. So this is where I just said, oh, well, this just means that the theta, which is equal to 2x, I needed 0, which is either at 0 or pi. So this is different because we don't have 0 on the right-hand side. If we had 0 on the right-hand side, I wouldn't need to change this. What's one way, though, I could approach this new equation? So option 1 would be I could subtract sine x from both sides, right?
Yeah.
So I'm going to have 2 sine x cosine x minus sine x equals 0. Could I divide both sides by sine of x?
Could.
I could. I'd have cosine of x is equal to 1. Which way seems nicer?
When you divide it.
When I divide it seems nicer?
I think.
You think? Okay. We're going to start here then first, and we're going to look at what's going to happen. So I would divide by 2. I'd have cosine of x is equal to 1/2. And now I have an inspection problem. Well, where does my x-coordinate equal 1/2? This is going to be at x is pi over 4, or 7 pi over 4. Okay. Let's look at the other side really quick though. So I've got 2 sine of x cosine of x minus sine of x. I've got a factor of sine of x, right? Both have sine x in them, so I can factor that out. So I have sine of x times 2 cosine x minus 1 equal to 0. So now I've got either sine of x equals 0 or 2 cosine of x minus 1 equals 0. Well, this we had before. This is the same as what's on the right in red. So this will give me x is equal to pi over 4 or 7 pi over 4. And now on the left, well, I think we've actually looked at when does sine of x equals 0. Yeah, so from before we know this is x is equal to 0 or x is equal to pi. So which one do we think is correct?
X equals 0 pi, I think.
So you're thinking this side is correct? Do you think the left side or the right side is correct?
Here's the left.
So can sine of x ever equal 0?
No. Or can it?
It can, right? At
Yeah,
0
it
and
can.
at 0 and pi it equals 0.
Yeah,
Wait,
Can
so
we-
it can equal 0 or it can't?
It can, because at 0,
and
so sine of 0, remember, is 0. And sine of pi is equal to 0. So I can't divide by 0, right?
Nope.
So then when we did, so since I can't divide by 0, that means that the right side won't work. Because over here I divided by 0, but I could have had, sorry, divided by sine of x, but I could have divided by 0. I'm going to put a question mark. On the left side, because we aren't possibly dividing by 0, I never once divided by sine of x. All I did was subtract and then factor it out. So when we're dealing with these problems, it is best to avoid dividing by a function like this to try and cancel it out. Otherwise we might have, in this case, so on the right hand side, we missed the fact that x can equal 0 or pi. And on the left hand side we got that it can equal 0 or pi. The right side accounts for the fact that, well, we divided by 0, which we can't do, but in reality we didn't need to divide by 0 at all. Let people try and write some of this down. Any questions with this one? We're just going to do one, maybe 2 more examples together. And then I think we'll do that one together. I'm going to give 2 problems for practice at the end of this, which will go over kind of these first 2 again. So we're going to look just at different types of identities we might use.
Mr. Bennett, after this next problem, I gotta go.
Okay, you're good. So the third one, we'll start by looking then at we're going to do 3 cosine squared of theta plus sine of theta is equal to 3. Okay. So this one might seem a little bit confusing. You might think, well, should I multiply by something? So this is when we're going to go back to alternatives for the Pythagorean identity. So remember Pythag, it's cosine squared x plus sine squared x is equal to 1. I can get alternative forms by either subtracting sine squared or cosine squared. I know I have cosine squared, so I want to find out what cosine squared equals. So I would subtract sine squared x to get cosine squared x is equal to 1 minus sine squared x. So this is where we're just going to do a substitution using our Pythagorean identity. And then this one will actually be nice and we can solve algebraically. So I have 3 1 minus sine squared theta plus sine of theta equal to 3. My next step is just distribute. So I have 3 minus 3 sine squared theta plus sine of theta equals 3. I can then subtract 3. So I'll have minus 3, negative 3 sine squared theta plus sine of theta equal to 0. And now all I need to do is see if there's a factor, which there is. This is essentially x squared, so minus 3x squared plus x. So really I have a sine in common. So I actually have sine of theta and then minus 3 sine of theta, not squared, sine of theta plus 1 equal to 0. I now have two factors. I can just set them both equal to 0, so I can have sine of theta equal to 0, which we saw gives us theta as 0 or pi. On the other factor, to have minus 3 sine of theta plus 1 is equal to 0. This would be solving just an algebraic equation, so subtract 1. So I have minus 3 sine of theta equal to negative 1. Divide by negative 3. So I have sine of theta is equal to 1/3. If you wanted to simply write right now, like I know not everyone may have a calculator, I gave the Desmos link which could do this for you if you wanted. So this would be theta is equal to sine inverse of 1/3. I'd specify in problems if I said it's fine to just stop at like an inverse function, because then it's just a matter of do you know how to use a calculator and identify the second angle. In this case, if I'm going to go pull up Desmos really quick. Well, I'm in the Spanish keyboard. Oh my goodness. Whew. I'm trying to press numbers and they're not giving me my numbers. 0.339. So if you had tried this in your calculator yourself, you would get theta is equal to 0.339 approximately. We know inverse functions are only defined in 2 quadrants. So we know this is going to be just one of our solutions. So I'd have to find the other by just adding pi to it to be able to get to the next quadrant. But this would be fine. How much time? Okay. I think that was Min. You said you had to go after that one?
Yeah.
Okay. So tomorrow is just the homework, which I'll post, but it's the homework from 6.6. So if you have your book and the paper still, you're good.
Okay. Alright.
Alright, see you, Min.
Yep.
We're going to do one last problem really quick, and then we'll be all set. Just as more practice, sine of x plus cosecant x equals -2. What is cosecant equal to in terms of sine?
One over sine of x?
Yep. I also wrote a little note. On the technicality, you might sit here and say, well, now we have dividing by 0. The book even itself says when sine of x does not equal 0. I'm going to add 2 to both sides as well. Okay. I want to be able to have just sine in numerators. So if I were to multiply the whole left side by what? How would I be able to do this? How can I get rid of sine of x in the denominator?
Multiply the entire left side by sine of x.
Yep. Sine of x. So I'm going to get sine squared of x plus 1 plus 2 sine of x as 0. So this is sine squared x plus 2 sine x plus 1 equals 0. We can now do that kind of substitution. I'll say this is u squared, so I'm not using x again, plus 2 times u plus 1 is 0. And then I just have to find factors, either by doing Pythagorean identity or doing just regular factoring. I know factors of 1 are just 1 and 1. 1 plus 1 is 2. So I have u plus 1 times u plus 1 is 0. So I have, for both of them, u is equal to -1. I'm going to say u equals sine of x. I can now put sine of x back in. And then I'm just looking for what angle gives me a y-coordinate of -1. And we know for this, the only answer is 3 pi over 2. This is number 4.
What does it say under the sine x equals -1?
Sine of x minus 1? I meant to write y coordinate, but I wrote y equals car.
Okay.
So this is coordinate. Any questions at all that we want me to go over? Okay. For practice, I gave 2 problems. These are a lot like numbers 1 and 2, where this is, I'm going to say A. I'm going to do this with my pen, not my mouse. So practice letter A is a lot like number 1, and practice letter B is a lot like number 2. This is almost the same, except it's a minus instead of a plus. So you're going to get some angles and then have to check if they work or not. And then for here, you're just going to use a double angle identity again.